ladies and gentlemen, welcome. My name is Denis Gonzalez, and you are watching the 60th installment of the scheduling seminar. So we have small anniversary. So there will be 60 talks and registered on our YouTube website. And today I'm happy to introduce Philippe Laborie from Hexaly. Philippe did his PhD in Las Toulouse in the robotics group with Malib Galab. And then he made postdoc at EDF, Électricité de France. And later on, he joined ILOG while working on ILOG scheduler with well-known people like Nathan, Claude Lepape, Laurent Perron, and Peter Willy. And later on, the ILOG company was bought by IBM, as many of you know, and they designed a new solver called CP Optimizer, which is, I think, a state-of-the-art solver in CP today, and solving many scheduling problems better than other algorithms. And in 2022, he joined Hexaly, and now he works on a new scheduling engine, which is quite popular. He likes to work on his garden and read literature. So Philippe, it is great to have you here. I think you're a very good speaker. Already I have seen many of your talks before when you have been at IBM. And the floor is yours.
Okay, so thank you very much, Derek. So today I will speak about Hexaly Optimizer and with a particular focus on scheduling. For maybe many of you do not know the Hexaly company. So Hexaly is a software company working in mathematical optimization and basically operation research, decision science. We are at the same time providing an optimization solver and a platform. And also we are working on developing application for our customers. So actually the solver is really very good at solving routing problem and packet problem and scheduling problem. In this presentation, I will focus on scheduling. We have more than 20 years of experience. We already have a large number of clients. It's about 200 clients. We have been developing about 400 applications, and we have many thousands of users in different countries. If to speak about the company itself, we are more than 40 employees. Among them, there are many engineers, so more than 30, and they share their time on developing the optimization solver and the platform, and also on developing models and applications for our clients. So this is very interesting because most of the engineers here have really this experience both in coding in the solver and in working on customer models. So this is a very good interaction between these two activities. We have offices in Brooklyn, New York, and in Paris. Here are some of our customers. This is not the explicit list, but you see that we have applications at Amazon. Well, I won't list all the companies that work with us. You have the slides, and this list is not complete. So if to describe what we are providing, the first thing is that we are providing an optimizer, okay, which is called Hexaly Optimizer. We also work developing a particular modeling language, which is called Hexaly Modeler. This is a very nice and easy way to develop your models. We will see, I will illustrate the presentation with some models written in Hexaly Modeler. We also have a studio, okay, that helps you developing very fast some application where you write the model in the language Hexaly, and then you can easily add some Gantt charts, some iteration with the user. We're also providing some services on the cloud to run the solver. So Hexaly Optimizer, now if I focus on Hexaly Optimizer, is really a mathematical optimizer. So here I make a difference between a problem-specific approach against a mathematical solver. Hexaly Optimizer is really a mathematical solver, and I hope you will be convinced about it in the end of this presentation. So here, the idea is that we start from the business problem. We write a mathematical model, okay, mathematical formulation of the model, and then there is an automated resolution to solve the problem. So if you can, if you work with MIP, for instance, this is typically the case of a mathematical solver. But we will see the difference between, for instance, a MIP solver and Hexaly Optimizer. So the schedule of the presentation is that we'll first very fastly describe some characteristic of industrial scheduling problems. What I didn't mention so far is that the Optimizer is really dedicated to solving real problems in the industry. Okay, so as far as scheduling is concerned, real scheduling problems. We will see that when we look at these scheduling problems, well, we will turn back to very basic mathematics, and I will illustrate a couple of concepts that sometimes are a bit overlooked when one speaks of a mathematical solver. And we will see that these concepts are very useful for providing very compact models for scheduling problems. Then I will focus on Hexaly Optimizer. I will illustrate a little bit the modeling language. I will speak of the resolution technique and then give you some idea about the performance of the solver. So if we speak about industrial scheduling problems, if you look at the characteristics of this problem and maybe sometimes compare with what is done in the academic literature, of course, there are sometimes some differences. Most of the industrial scheduling problems are heterogeneous in the sense that you have, in the same problem, you have different types of resources. So you have disjunctive resources, cumulative resources, inventories. In most of the problem, you also need to allocate the activities on some resources. So there are some decisions to allocate well, the activities on some resource. There are many types of different constraints. Of course, there are temporal constraints, but there are also calendar constraints because especially when you speak of human resources, they do not work all the time. They take some breaks from time to time. This is just an example. Quite often there are very complex setup conditions. If you're considering tasks that are executed by a disjunctive machine, so in between the activities, there are some setup constraints that should be represented. Quite often, you need also to represent some batches, which is a group of operations that you can batch together, okay, and then perform together. As far as the different objectives are concerned, actually, in the industry, using a max-span as objective is not very uncommon. Most of the time, the costs are tardiness costs. Quite often, there are allocation costs on the machine, there are setup costs, etc. Another characteristic of these problems is that the sizes, I mean, they are large. For instance, we handle problems with up to typically 1 million activities and say 1,000 of resources. This is some, I would not say it's common problems, but it is realistic problems. Also, one thing is that the granularity of time can be very small. For instance, you could have 1 million of time points in the horizon of the schedule. So in this case, and this is something that is well known, I think, is that MIP technology does not scale well on this type of problems, especially when you speak of large problems. Okay, it's okay if you're solving problems with 100 tasks or a bit more, but as soon as you scale with very, very large problems, well, it doesn't scale. The reason is that you need to have quite often a quadratic number of variables. For instance, if you want to model a disjunctive resource, and you have booleans for each pair of activities on the resource, then okay, if you have a machine with 1 million activities, you see that we have 1,000 of trillions of Boolean variables, and this is cannot be handled in a big model. And it's a bit the same problem with discrete time formulations. So one of the goals of Hexaly Optimizer is to try to be able to provide the concepts to have models that scales linearly with the size of the data, okay, to avoid this quadratic or even worse effects on the size of the model. And of course, to be efficient to solve this model. So in order to do that, I will jump a little bit back to basic mathematics, okay? So one thing we learn when we start at elementary school is the notion of number, okay? 1, 2, 3. This is the notion of comparison between numbers. 2 is more than 4. Then we learn addition tables, multiplication tables, okay? So this is on the right side of the slide. I wrote basically what you can do with these concepts. And this is basically MIP, okay? Mixed, integral linear programming. I don't know you, but for me personally, I hate mathematics at elementary school. Just because it was boring to learn tables and so on. And then at secondary school, at least in France, at my time, we started to learn some very interesting concepts that really make me to be very fond of mathematics, let's say. The first concept is the one of set. So you have a set of objects. What is nice with the notion of set is that you can manipulate set without knowing exactly what it is inside the set and without having to enumerate what is inside the set. So you have the notion of set, here A. You have the notion of an element that is contained into a set. You have notions like cardinality of the set, inclusion between sets, partitions. Okay, you could say that a subset of sets B, G forms a partition of a set A. So maybe as you are very experienced in scheduling, you can see that, for instance, many scheduling problems can make use of this notion. For instance, if you have a set of machines on which some activities can be executed, and then you need to select one machine, you may have the notion of the set of activities performed by a given machine, okay? So, and if you consider all your activities, you want to partition them into some subsets where each subset corresponds to the activities executed on the machine. Okay, if we go a bit more deep into this, we also have the notion of permutation of a set, of the elements of the set. Okay, so let's say SA is a set of permutation of set A. So again, you may have a sigma, which is a permutation of this set. You might want to know which is the element at a given position in the permutation. And also what element is at a given position in the permutation, or which is, let's say, the fifth element in the permutation. Of course, again, when you think of scheduling, this is very useful to have a permutation of if you say that in a set, the element in the set corresponds to activities, well, a solution to a unary resource, to a disjunctive resource, will be a permutation of this set. Okay? Then maybe the last thing we can consider also is the notion of interval. So an interval is an interval of, in Hexaly, it's an interval of integers. You have the notion of the interval itself. You can see the interval as a set also. So you can see that a given value, for instance, let's call it t, belongs to this interval. But you also have some basic operators on intervals, like, for instance, taking the convex hull of a set of intervals. Okay, and of course, as you may guess, typically intervals are used in scheduling problems to represent activities. So we will have the notion of the start value of an interval, the end value, and the length, which is just the end minus the start of the interval. Maybe last notion that we learn at school is the notion of function, which is very useful. Let's say we have a function ft. In scheduling, it can be used to represent what typically the level of a resource or the level of an inventory over time. Okay, And here again, we want to provide this notion of function, but without to having explicitly to describe what is the value of a function for each time point t, okay? So those are the concepts that are used in Hexaly Optimizer. So now if we, now we'll focus on Hexaly itself. Now I have explained a little bit the mathematical, very simple mathematical notions that are used. Hexaly Optimizer is, so it's an optimizer. You can define your model in many different languages, like Python, C++, Java, C#. And also, as I mentioned, we have a specific model, specific language for entering the model, which is called the modeler. And whatever the language you use, it always, you always have inside the solver a unified description of this model. And this is the same whatever API you use, okay? So these concepts in the model are exactly used on the notions I described just before. We have numerical variables like Boolean, integer, floating points. We have set variables. So we have lists, which are the same like permutations variables and interval variables, okay? And what we define on top of that is that we just define the classical algebraic operators or set theory operators on these different type of concepts. Like, of course, if you have numerical variables, you can use a sum. If you have a logical Boolean variable, you can use AND or. If you are using collection, you can make union. If you are using interval variables, you can have else of interval variables. And this is the only element of the language. I will dive a little bit into this soon, but there is no need to introduce more aggregated concept. If you are used to optimization solvers, especially for scheduling, that are using constraint programming, quite often you need to know what are the different global constraints that are available. For instance, you may have some cumulative constraints or whatever. We don't need that in Hexaly. We are working really at the level of mathematical concepts, and we will see some examples. So, except for that, Hexaly Optimizer under multi-objective optimization, so you can have lexicographical objective. Something that is sometimes important, but I will not focus on that today, is the support for black box functions in the model. You're not obliged to explicitly describe the model with predefined expressions. You can also use functions that are called automatically and that return, that you write yourself and return some values. Now the engine also supports initial solutions, which is often called as warm start in MIP, for instance. Okay, so now I will illustrate the different type of decisions. This uses the Hexaly modeling language, but of course you have completely similar thing in all the languages, in Python, in C++ or whatever. So these are the different numerical variables. That's pretty simple. There is not much to say. You have Boolean variables. An example of possible value is true or false. We have integer variables, and we have floating point variables. So this is pretty common in many solvers. What's interesting is the notion of sets, as I mentioned, and list variable. So you can define in Hexaly a set variable. A set variable is here on the left. A is a subset. The value of a set variable is a subset of 0 of the integers, 0 until n-1, okay? So for instance, a value, if I have a set variable defined on n equals 6, possible value for the set in a solution could be the sets that contain only the values 0, 3, and 4, okay? There are other values here. Well, in this picture, implicitly, there is a partition, and where you have 3 sets, but of course, the sets can be anything. But the value of a set, what you have to keep in mind, the value of a set variable is a subset of integer between 0 and n. Okay, and so the number of elements in the set is not known in advance. A bit similarly, a list variable is something of the same kind, but the ordering in the list matters. Okay, so if you define a list on 6 elements, then a possible value here is a list that starts with 0s and 3s and 4. Another value for the same list actually is okay, it starts from 1s and 2s and 5. Okay, so those are decision variables in the problem, and you can define this type of decision variable in your model, in your scheduling model. The other type of decisions is the notion of interval variable. So you can define an interval variable x between minus, let's say here, minus 1000 plus 1000. And here it's a possible value. The interval starts at 200 and finishes at 600. So here, the two numbers give actually the minimal start time and maximal end time of the interval. Okay, so this is a possible value for x. Now, if you remember, I mentioned that, in fact, the model, okay, is just a mathematical model specifying the classical algebraic operators between all these concepts. So if we focus on numerical values, so of course we have floating point variables, then there are all the most of the arithmetical expression on floating point variable, like of course sum, minus, the product, and so on, whatever you want, log, exponential, trigonometrical function, etc. So this is internal to the set of floating point expressions. Now you also can take the sales, the floors, around. This will brings you to the world of integers, where you can also combine the expressions with sum, product, etc., min, max, absolute value, integer division, modulo, and then with all the relational operators. This can bring you also in the worlds of booleans, where you can combine your expression with and, or, etc. This is concerning the numerical expressions. But then on top of that, as I mentioned, we have sets and we have lists. These form kind of collections. So for instance, on a set, you can ask whether or not the set contains a given element here. And this is a Boolean, obviously. So this is an element expression in the classical set theory. Okay, and so maybe I will not describe everything, but you can count. This is the coordinality of a set. Okay, so if you have a set variable or set expression, you can call count on it, and it will give you an integer expression that represents the cardinality of the set. There are things like, for the list, you can also take the value of the list at a given position, okay, or the position of a given element in a list. This is an integer. Concerning the intervals, you can take the start, the end of the interval, and then there are also some operation between the sets. You see, you can take the union, intersection of sets. You can also count the distinct element. If you apply a transformation to your set, then you count the different. You can have the distinct element after this transformation. I will have an example. And that's about all. So on this picture, you see most of the language available in Hexaly Optimizer. Of course, we can define also some arrays of these elements. And what is very, very useful and very powerful is that all the n-ary operators in these algebras, like the sum, the max, or whatever, the or, the scope of this operator can be variadic. It means that the scope can be a variable collection. So suppose, for instance, you define a set variable like this, x is a set variable. You don't know exactly how many elements there will be in the set, okay? This is part of the decision of the problem. But you can have an expression that is, for instance, suppose that each element in the set have a weight, which is given in an array. You can compute the total weight of the set by summing up over the set X, and this is a lambda expression. And for each element I in the set, you will sum the weight, okay? So even nicer in a way, if you want to count, if each element has a color, let's say the element has a color, as known color, you can apply an operator distinct on this set X. This will return the set of colors used in the set X, okay? And then you can reason on these colors. I don't know, maybe you do not want in the set more than 2 colors. So you could put a constraint that counts the color, the cardinality of colors, and say, okay, it's less than 2. Okay. This is mostly about the concepts. Now I will illustrate some of the how we can use this language for modeling scheduling. Of course, one scheduling problems. A typical example is for modeling a precedence constraint between 2 intervals. So here we define 2 intervals, x and y, and we pass the constraint x is lower than y. It means that all the value is in x. This is in the algebra of intervals, if you want. So it means that x, the end of x is smaller than the start of y. But of course, you can write constraints like the end of x, which is an integer expression, plus a delay slower than the start of y. Here, the delay can be any expression, okay? It can be very complex, can depend on many other decisions. Of course, you can constrain the length of an interval. If the interval represents an activity, this would be the duration of the activity. But you can do some very interesting different things. For instance, there is a concept of a function. You can consider this is an array, working is an array that at every value t gives a 0, 1 value describing whether or not, let's say, a resource is working at this time, okay? So when it's 0, the resource is not working, and when it's 1, the resource is working. And you want to constrain the work duration of the interval, of the activities. So what you will do, we're using the same type of variadic construct. We will sum over the interval. So here we see the interval as kind of set, okay? And for each value t, we will sum. So this is the value of working at t. This is exactly the same as computing the integral between the start and the end of this function here. And you will say it's equal to the work duration. Okay, you can also use this, for instance, if you have a cost, if during the execution of the activity X, if X is an activity, you have, let's say, a price of electricity, for instance, and then at each time point, you will use the quantity of electricity at this price, then the total price of the total cost of the activity will be the sum, so the integral of this price function over the activity. And this will be an integer expression that you can use in the objective, for instance. Speaking of objectives, this is how you model, well, a max. Obviously, it's a max over the end time of the end value of some intervals. If you have some weighted sum of tardiness, which is much more common than max span, that this will be a sum of a weight times, okay, max of some between 0 and then time of the variables minus the due date. But you can have some much more complex expressions that the net present value, in case you are dealing with scheduling with financial aspect, then the net presence value will depend on the end time of the interval, and then it will be a power, an expression using an exponential. You would write it this way. Now, let's say something maybe, I would say more interesting, but interesting in any case, is how we model a disjunctive resource. First, you will build a list that represents a sequence of activities in the resource, okay? Here, for instance, suppose you have a disjunctive resource with n activity. We define a list over all the possible indexes of the intervals. Okay, you would define the interval variables. Here, if you want to execute all the activities in the list, you would say that the cardinality of the list is equal to n. So here, all the values of the list will include all the elements, but the difference will be the permutation of the elements. And then you want to link the value of the list to the timing of the intervals. So the only thing you have to do here is to say, okay, with the variadic function between 1 and n, you want to say, given a position in the list, the interval at the I-1 position in the list is before the interval at the highest position in the list. And that's all. It's very important to see that, in fact, this construct does not, it is in link with what I mentioned about having models that scales linearly with the size of the data. This construct, there will be only one construct per resource, okay? There is nothing inside that really, would be, Boolean variables for each pair of element in the list or whatever. Okay, this is really a very compact formulation and compact in the engine model too. If you have sequence-dependent setup times, well, you would just add this constraint saying that the end time of the previous element activities in the resource in the list plus the setup time between the two consecutive elements is lower than the start of the next activities on the resource. If you want to minimize setup cost, well, this is almost the same thing. You will just minimize the sum of this setup cost matrix, which is indexed by the previous and the next activities on the list. Okay. Quite often, we don't know. We need to allocate the activity on the machine. Okay. So this is where the notion of list with variable set of elements is useful. Here, let's say we have m machines. So we define m lists, okay? We would have n intervals, so n activities. And then each activity correspond to an index in the lists. But we want to say that all these lists forms a partition, okay? So if we have two machines here, and if we have, let's say, 5 elements, a possible solution could be this. It satisfies the partition constraint on the list. And then we have, again, the disjunctive constraint, I would say, relating the list values with the interval variables. Okay, saying that between 1 and the count, so the cardinality of the set, here, the cardinality is not known in advance. Okay, it will depend on the side and how the intervals are partitioned in the list. But for each list, the set of consecutive intervals follows the precedence chain. Okay. Of course, using this mathematical concept, you can use the notions of the fact that an element is contained into a set or a list to express things like you have a machine that is compulsory for let's say, activity 3 really need to be executed on machine 0. So element 3 must be contained in the list. Or if your machine is impossible, you say that element 2 is not contained in this sequence. You may have also complex dependence constraints like implications. Say if activity 1 is executed on machine 0, then activity 4 is not executed on machine 1. Those are logical constraints, and they are the fact that it is an element in the set theory. Okay, you can express also some resource-dependent features, like the length of an interval variable will depend on which machine the activity is allocated to. This is this kind of expression here, find, that I mentioned in the slide, some slides ago, and it tells what typically if you have a partition on the sequences, it means which elements of the partition the element belongs to. So it means that here, with the scheduling semantics here, which machine executes the activity. Okay, so it's pretty easy with all this mathematical concept to express many things compactly. For instance, suppose also that you have two tasks with a precedence between them, but the delay between the precedence will depend on which machine the tasks are allocated to, because you have some transportation time between the machines. The machines are not at the same place. So you may have some travel time matrix that is indexed by two machines. And then here you have a precedence constraint. And that depends on the position of the machine, typically. Okay, now let's have a look at how we formulate cumulative resource, because it's also very interesting how we can formulate cumulative resources with only using the mathematical concepts I mentioned before. So again, we do not have a cumulative constraints or things like that. If you see the definition of cumulative resources, the definition is classically, we want to say that at any time t, the sum of the weight of the contribution of the tasks that are running on the resource at this time must be less than the capacity of the resource. Okay? So suppose that you have interval variables representing the activities running on the resource. You want to say, okay, at any time t, so you will iterate, you will post a constraint. So this is a variadic constraint. So between, let's say, the horizon is 1000, between 0 and 1000, for each time point t, you will post a constraint that what? The sum. I will really highlight different aspects in the sentence. The sum of the weight of the tasks, E, so this is supposed to be a data, this is a contribution of the task, that are running on the resource at this time t, so that it means that such that value t is included in the interval, is lower than the capacity of the resource. Okay? But you have to keep in mind that this constraint is written in intention, and that never in the solver we will unroll this loop on t. Okay, because this is just this type of pattern typically will be handled by the solver itself. The scope of this type of constraint does not have to be a constant. Maybe you have a makespan and you want to constrain only the resource over the makespan, or maybe you want to constrain only the capacity over even a variable interval in the schedule, which is the decision itself. So there's no problem. This is this variadic constraint. The capacity may also, of course, be time dependent if you have a capacity profile. And the scope itself may be a variable set, the scope on which you will sum the variable. Suppose that you have kind of flexible problem where the task can be splitted on different cumulative resources. You do not know in advance the set that will be executed on a given resource. This will be a set variable, but you want to say that at each point t, if you sum over this set variable the total usage of the resource, then it must be lower than the capacity. So you see that we do not need to introduce any specific concept related to scheduling. It's only pure mathematical concepts. This is an example of the RCPSP, the model of the classical RCPSP. I guess you all know the problem. So we will define one interval for each task. We constrain the length of the task to be equal to the duration of the task. We have precedence constraint here between the tasks. If we want to minimize the max span, this is the max n times of the task. And then this line is the cumulative constraint. So at each time point t between 0 and the max span, the sum of the usage of each resource by the task is lower than the capacity. Okay. And now we have seen, I think, everything about the model. And I've given some hints on how to model several aspects of scheduling problems using the mathematical language. Concerning the resolution, so I said that we start from the unified mathematical model, and then we have many different type of exact and heuristics algorithms that are run. They can be run in parallel, they can be run in sequence, and they basically exchange some information, so some solutions, some bounds, things like that. if we're looking at the different techniques that I used, it's difficult to describe everything because there is a huge number of different techniques that I used. Just to focus on a couple of things, we are doing a lot of pre-processing and reformulation of the model all over the place, because as I mentioned, we have different algorithms running. Each of them have different characteristics. They have their own modeling concepts even. So there is some pre-processing already at the, let's say, the higher level of the model, but then there is also some pre-processing and reformulation in this algorithm. Some of these algorithms use some simplex. So I highlighted here most of the concepts that are used for scheduling application. Simplex is used to compute some relaxations of the problem, and for instance, to provide some bounds. We are using constraint propagation, obviously, some heuristics, different type of heuristics, and in particular, we are able to recognize in the problem some particular well-known scheduling problems. For instance, some well-known one-machine scheduling problems on which we have polynomial algorithms to produce optimal solution, and we can use this optimal solution either to provide bounds for the problem or to guide the different heuristics. So we are using large neighborhood search, local search. All these techniques, in fact, they need to be configured. And we are also using a lot of statistical learning techniques during the resolution to auto-tune and auto-configure the search. Okay. So now let me say, and we are going towards the end of the presentation, I want to say some words about performance, because it's nice to have a very generic solver using very general mathematical concepts. But most of all, once we have expressed the problem, we want to solve them and to be efficient at solving them. So there are some comparisons. You will find many benchmarks on our web page that we'll mention later on. I just wanted to give some highlight on some problem. This is a benchmark on flexible job shop. We took most of the classical instances of this problem and compared against here it's Laborie. We like to compare after 1 minute of CPU time, okay, because we obviously want to provide very good solution very fast, okay. And here, in this case, this is comparison between Hexaly and later version of Laborie. We provide here the gap. So it is a gap. It is a gap to the best known solutions for each of these problems. And main idea is that with Hexaly, even for the largest problem, even in only 1 minute, we are very close to the best known solution for all the instances. This is also the same kind of comparison for the largest, let's say some medium-sized RCPSP programs with 300 tasks, which is already something that is not completely small compared to the literature. But here also we see that we very often obtain after 1 minute a gap that is very small. Typically for, let's say, 41 of the instance, we end up after 1 minute with a gap that is less than 1% compared to the best known solution. The best known solution, quite often they are run with very large time limits. So, having a gap lower than 1% is pretty good. So there are some different kind of benchmarks. Another thing is that, as I mentioned at the very beginning, we want to be able to scale on very large problems. So for instance, there is a benchmark of very large job shop with 1,000 jobs, and each job consists of 1,000 operations. So we have in all 1 million operations and 1,000 machines. This time for this type of problem, we let Laborie run 10 minutes, and we compared against here mostly Hexaly Optimizer with 6-hour time limits. And we see that in general on this benchmark, we find solution. Well, the instances are pretty similar. So I don't know if it's very relevant to look at the different instances, but we have 8-10% better objective already after 10 minutes. And we are able to provide feasible solution very fast, even for the huge problems. And many of the solvers, I don't speak of MIP problems of MIP solvers, but of course are not able to find any feasible solution to this type of large problem. We have been working, and the solver is constantly improving. So for example, here, we had been working on improving the lower bounds on some scheduling problems. And here you see the decrease of the gap between two versions of Hexaly on some classical scheduling problems. So we end up with finally quite small gaps, even for large problems. We are able to find quite nice lower bounds. Okay, so this is about the end of the presentation. If you check on hexaly.com, you will find many other benchmarks with details, because you had no time to describe the details of the benchmarks on different problems, scheduling, routing, etc. And also, if you're interested in seeing some model in Hexaly, we have a very exhaustive example tour and the documentation in the website. So I think we have about 50 different type of problems. So each of them, you have their model in Hexaly modeler, and in a different API in Python, in C++, or whatever is your favorite language. And I think that's all for me.
Okay. Thank you very much for this informative talk about successful industrial product, which is, I think, very close to academia. So now let me open discussion. I will allow everybody to ask a question. So now everybody should be able to unmute, if I'm right. So should you have any question, don't hesitate to ask.
Let me ask a quick question, Philippe. Those benchmark problems, the large job shops, the 1,000 jobs, the 1,000 operations, and what was the objective function there?
Oh, Makespan it was, yeah.
Makespan?
Yeah.
Oh, so you haven't looked yet at total weighted tardiness, just
No.
an easy objective function.
No, it's pretty easy to try. Yeah, I think, honestly, I think that so we improve on other solvers, but still, even for Makespan, the quality of the solution is not, I mean, I'm pretty sure there's a lot of progress we can do on the quality of the solution itself.
Because I think that among your clients, for example, if one of your clients is semiconductor manufacturing, the objective function that's the most, it's total weighted tardiness.
Absolutely.
And that's a little bit harder.
I cannot agree more with you. Yeah. Sure.
Okay.
Makespan, as I mentioned, in the industry, we almost never see Makespan optimization.
Yeah.
Weighted tardiness is something very much more common in the semiconductor and many industries. Yeah, and many objectives.
Any other question? There are some questions in the chat, so if you can open it. If you can open chat.
Okay.
Read the question, please.
Yeah.
Well, I can read the question.
Okay.
Can Hexaly provide optimality and provide optimality gaps?
Yeah. Yes, it can. It can. It really depends. The quality really depends, of course, on the problem, because proving good bounds is very challenging. But yes, it can, of course, prove optimality. For instance, let's say mention on the, it's come just to my head, but on the open shop problems, there is some classical benchmarks, and then Hexaly is able to close all the instances pretty easily. So yes, the answer is yes. Hexaly can prove optimality and produce optimality gaps, and we always show some optimality gaps. Okay, and then sometimes, but this is not particular to Hexaly. Sometimes the gap is large, but quite often it's because the lower bound, for if you speak of minimization, that the lower bound is not wonderful, but we provide gaps. Yeah.
Okay. The next question is from YouTube by Irf Lustig.
Yeah.
So the question is there a dictionary that could help convert an existing CP optimizer formulation or Google CP SAT formulation for scheduling to Hexaly?
No, we do not have that. We do not have that because it would be some work, because you see we have all these lambda expressions that we would have to unroll in order to provide kind of, let's say, flat model. But if someone wants to do that, it could be a good thing.
The next question.
And there was a second question I see from Earth. Yeah, good question. Do we have the notion of presence of an interval? So currently, the interval variables in Hexaly, they're not, because if the reference is to CP optimizer, where there is a explicit notion of optional interval, in Hexaly, currently at least, this may change, but the interval are not optional, they are present. But in order to model the possibility for an interval to be optional, we're exactly using this notion of sets and lists, okay? Because this is equivalent to a certain sense to the fact that the element belongs to the set, okay? So when in the small example I mentioned about flexible machine, where we have to select the machine, we could model this with optional intervals, but with Hexaly, the fact that an interval of activities executed on the machine is represented by a contains constraint, Boolean constraint.
Okay. Then the next question is by Florian from Airbus. If the program is not solvable, does the Hexaly solver provide insightful reasons or explanations to help the user in order to help them debug their model?
Yes, it does. You can call the computation of inconsistency core in the solver when the model is infeasible. So it exists. We can use that, provided that currently, because this is also something that, we're currently working on improving all the feature of Hexaly. If the model is trivially infeasible, if you can detect this infeasibility very high in the model, then it will work perfectly, and then you will have a minimal set of constraints that is infeasible, okay? If the infeasibility is a bit more hard to prove, then this may not work exactly as expected. But the answer is yes, we have a way to discover inconsistencies in the model and explain why a model is inconsistent.
Yes, so the next question is quite difficult by Ryan. I will try to read it. So I think the number of algorithms used in the underlying engine is very interesting, period. If we have very efficient algorithms to solve similar models to what goes into Hexaly without the detailed resolution, an algorithm that solves an LP relaxation of a simplified scheduling model, is there anything we can do to feed in that solution information into Hexaly to guide the scheduling to get solution quicker? Something like warm start maybe, or?
Yeah, I understanding as warm start. So yes, we use a warm start. You can just give some values to some decision variable of the problem. It's not necessary that you have values for all the variables. It's not necessary that the solution is feasible. If it's not feasible, the solver will try to exploit some information in this warm start. And it can be useful in scheduling if you're rescheduling, for instance, and you want to have a solution that is not too far from the previous solution. This can be or exactly as described by Ryan, if you have a relaxation or over-constrain the program and then get a feasible solution, or have your own heuristic to provide an input solution, then yes. And it's pretty simple to use.
Interesting. And David Gravot, are pure constraint programming techniques the main block for your scheduling examples, or does Hexaly rely intensively on much more algorithms there? The constraint programming is like dominating probably the
constraint programming is main. I know it's also there are two or three things maybe, but two things when on pure scheduling problem, let's say. So there are constraint programming techniques, and this is usually what helps finding solutions and quite decent solutions very fast. And then they work in cooperation with some more local search algorithms that try to repair the solutions, and by repairing them, try to find the better solutions. And I would say those are the two main algorithms that helps. And what we see is that quite often constraint programming produces some solution, improves them, but then gives this solution to some local search, which try to repair and locally modify the solution to get better solutions. But we are also using large neighborhood search in the constraint programming techniques. So yeah, it's...
Yeah, and now we are speaking about scheduling problems. What about, for example, vehicle routing problems? Is there a situation completely different because CP is not very strong in TSP typically? Right?
Yeah, absolutely. So in this case, there are, let's say that if the constraint is considered as a transportation problem, the techniques that are used and some algorithms that are used are completely different. And for routing problems, they will be more focused on local search algorithm. Yeah.
Okay. One more question by Ahmed Kashiba. Any reinforcement learning techniques under the hood? Or do you use them, for example,
Yes.
for this
Yes.
or could you mention on that?
Yes, the idea is that we have different methods. Well, I've seen we have a myriad of different methods. Each of these methods may have different set of parameters, and inside the methods we have also different ingredients with different parameters. And especially, for instance, for the constraint programming techniques, we are using some reinforcement learning to auto-configure the search on the different ingredients that works the best for the problem that is currently being solved.
Okay. Okay.
So I just try to avoid doing something that doesn't work at all, typically.
So then, David Gravot has another question. Are variadic concepts, very powerful expressivity, adding lots of complexity to the search?
Yes. So it depends on which type of algorithm we are working on the problem. It adds some kind of complexity in a sense, because it's also complexity in the code, let's say. For instance, if we are speaking of local search algorithm, they try really to work directly on the variadic concept and then to do some incremental reasoning on the variadic concept when you change some values of some variables in order to very fastly evaluate the concept. When we are talking about constraint programming, there is also here the variadic concept a little bit, let's say, unrolled in the search, and we are more trying to recognize some patterns, some variadic patterns in the model, to try to, under the hood, have a model that is that can be more easily handled by constraint programming techniques.
Okay.
I don't know if the answer is clear, but
it had complexity. Not so
easy
to respond properly, right? And also,
but it had also some terrible advantage, especially, for instance, in local search.
It's not so easy. There are many algorithms and many complex problems to be answered in very simple answer, right? So thank you very much, Philippe. What I like the most is the simplicity in which you describe the problems. The modeling language seems to be like very basic mathematics. It little bit makes scheduling more understandable, I think. That's really good. Okay, one more question.
That's exactly I wanted to focus on during this presentation, because it's really mathematical solver.
Yeah, so one more question. So by Laborie, you mentioned scheduling of up to 1 million activities. What is your experience? What are the challenges? Do you get reasonably quick, good solutions? For instance, having cumulative resources? With 1 million activities?
So with cumulative resources, we also, I did not show it, but so maybe not 1 million because the complexity is a little bit high, but with several hundred thousands of activities on some RCPSPs, for instance, we tried, and it works, because the idea is that we are very, speaking of constraint programming, we have also a focus in Hexaly on very light propagation, an extremely light propagation, and very fast. So this is how we can produce solution for these large problems. The challenges is now, well, as I mentioned, we can provide solution. Still, I mean, it's not clear that the quality of the solution is one of okay.
Sure.
Optimizing the solution and finding very good solution for these problems is still challenging, and we're working on it.
And when you say light propagation, you mean very fast, right?
Yes, very fast.
Okay.
Only really having the minimal thing that is useful for producing solutions.
Okay, any other question? If not, thank you once more, Philippe. It was really exhaustive, and I think that you are really on a very good track in your company. And now let me mention the title of the next talk. The talk will be given by Norbert Trautmann from University of Bern on 4th of December. And he will speak about mixed integer linear programming for project scheduling with resource unit related constraints. Thank you very much for being with us. I think it was very informative. We had over 40 viewers on Zoom and some more on YouTube, and I hope that you will join us in 2 weeks as well. So thank you very much and goodbye.
Thank you.
Thank you, everybody.
Bye.
Thank you.